Now let us see the same in the octahedral complexes. Now octahedral complexes must be having 6 ligands. So let us see first in octahedral complexes. Now octahedral complexes with general formula Ma2B4, Ma2B2, they shows this type of isomerism. Now what is this Ma2B2 here means? A will be unidentate, A and B both will be unidentate ligands, whereas in this case your A will be your unidentate ligand and B will be bidentate ligand. Now let us see how we can have this type of isomerism in these type of compounds. Let me give one example. Like let us take Ma2B4. Like this compound. This is called tetramine dichloridomanganese 2. Now in this we will go for the unidentate ligands which are present in lesser number. Now any one of those, when those ligands are present opposite to each other like this one, like maybe these two positions or these two positions or these two positions, and the rest of the 4 ligands are like this. We call this type of arrangement as trans isomer. Why? Because the ligands, by unidentate ligands which are present in lesser amount, are opposite to each other. Now when they are present very close to each other like this one, we just call it a cis isomer, because they are not opposite, they are just present on the same side or they are present close to each other. So this is what we have, the cis trans isomerism in octahedral complexes with the formula Ma2B4. Now let us see the same type of isomerism in the compounds with the formula Ma2B2. Now in Ma2B2, as I have told you, the B will be your bidentate ligand. We can have the example of we can have this compound, force 2 plus. See, it is diaqua bis ethane 1,2 diamine iron 2. Now in this case, this is a bidentate ligand, which is ethylene diamine or your ethane 1,2 diamine. Now how we can draw its cis and trans isomers? In this we will always consider your unidentate ligands, and when they will be present opposite to each other, that particular type of arrangement will be called as a trans isomer, rest will be called as cis. So it can be arranged like this. Suppose we are having like the 2 water molecules are like this, and we can have ethane bidentate forming bonds like this. So this type of arrangement is called trans. Whereas if we have arrangement like this, it is called cis, because they are present on the same side or they are more closer to each other. So it's called cis, this one is called trans. So this is what we have, the 2 compounds or 2 types of the octahedral complexes, which shows your cis and trans isomerism. Along with this, we have another type of geometrical isomerism, which is called facial meridional isomerism. Now it is only shown by octahedral complexes with general formula Ma3B3, where both A and B are unidentate ligands. Now let me give an example of this type. Like let's suppose we have this compound. This is called triamine trichloridochromium 3. Now in this case, the 3 amines or 3 chlorines can be arranged like this. We can have this type. Now in this case, what we find is no two same type of ligands are opposite to each other in this kind of an arrangement. No two same type of ligands are opposite to each other, and when we join them, what we find is out of the 8 faces, one whole face is made by the same type of ligands, and exactly their opposite face is made by the another type of ligands, but no two same type of ligands are opposite. Now this type of arrangement is called, or this type of the isomer with, or the compound with this kind of an arrangement is called facial isomer. And we can have similarly this kind of an arrangement. Now in this, what we find is this whole xylene equatorial chlorines are cutting this compound into 2 halves, and this amine is also cutting into 2 halves like a meridian, and these 2 same type of ligands are opposite to each other. So this kind of arrangement is called meridional. So this is what we have, the special other type of the geometrical isomerism called facial and meridional, which is only shown by the octahedral complexes with the formula Ma3B3, and these are the 2 its isomers described in the form of their structures. Now let us see the second type of stereoisomerism, which is called optical isomerism. So we know optical isomerism is a type of stereoisomerism in which what we find is the compounds are found to be optically active. They rotate the plane of the polarized light either to the left or to the right. Now those compounds which rotated towards the left hand side are called what? Levorotatory, and they are denoted by a sign minus, and those who rotated on the right hand side are called dextrorotatory, and they are given by a sign plus. Now what we can do is we can easily differentiate the two experimentally only. They can be differentiated by just by seeing. Now this optical isomerism in coordination compound is only shown by octahedral complexes. It is only shown by octahedral complexes with general formula Ma2B4, Ma2B2, Ma3. In this, A and B are your unidentate ligands. In this, A is your unidentate ligand, B is your bidentate ligand, and in this, A is your bidentate ligand. Now what is the important condition for a compound to be optically active is that it must be non-superimposable on its mirror image. And that is how, if any compound is non-superimposable on its mirror image, then those 2 compounds basically shows optical isomerism, and the 2 will be, one of those will be the dextro, other one will be the levo, and the 2 are together called enantiomers, as we have done in the case of organic chemistry. It's the same thing. Let us see these formulas one by one. Let us take the example of we have, let us take this one minus. Now in this case what we have is it's diamine tetrachlorido cobalt 3, cobaltate 3 because it's an anion. Now in this case we have 2 ligands of one type, 4 ligands of the other type. We will go for these two types of ligands. We have done the same formula in cis and trans isomerism also. Let me draw its one isomer, and then you just predict that what type of geometrical isomer I have drawn here. Now I think you can easily guess this. It's a trans isomer, yes. Now if we take this trans isomers and if we draw its mirror image, it will be like this. Now if I put this compound on this one, they both are found to be exactly superimposable on each other. So what we find is these are optically inactive. They are optically inactive. Why? Because they are superimposable on each other. So what simple conclusion we can draw out of this is all trans isomers are optically inactive. Optically inactive. So therefore now we will draw its cis structure. Like we can have the 2 amine on the neighboring positions, the 4 chloride on the other side. Now if we draw the like this one. Now if we places this compound on this one, we find that the both are non-superimposable. So yes, they are optically active. One of these will be plus dextrorotatory, the other one will be minus levorotatory. We cannot predict which one is plus and minus, we can put it any by like this only, and they both together are called enantiomers. The optically active isomers which are non-superimposable mirror images of each other are called enantiomers. So this is what we have. So these are enantiomers with the formula Ma2B4. Now let us see the enantiomers with the formula Ma2B2. I have explained you the reason why the square planar or the tetrahedral doesn't show this kind of optical, because only those compounds can show optical isomerism which doesn't contain any elements of symmetry. So a square planar or tetrahedral contains one or the more elements of symmetry, so they can't show optical isomerism. Now let us see the formula Ma2B2. Let us take in this this compound which is called dichlorido dioxalato ferrate 3. In this, oxalato is a bidentate ligand. So now how many isomers, stereoisomers are possible for this compound? It will be showing 3, or this formula, it will be showing 3 isomers. Remember, one is cis, another one is trans. Trans will not have any its optical isomer, but the cis one, whether it is plus or minus, will be having its another enantiomer, plus, minus or plus. So in total it will be having 3 stereoisomers. Now how can I draw its structure? It will be like this. Obviously we will draw only its cis form, and we can join oxalato like this, which is a bidentate ligand. So we can have the structure like this, and we can have 2 chloridos like this. This one. So any one of these will be plus, other one will be minus, and these 2 are enantiomers. The last type of example which can show, or with the general formula which can show the optical isomerism, is Ma3. Here A is a bidentate ligand, and we can take the example of this complex, which is tris ethane 1,2-diamine cobalt 3. Now in this case, ethane 1,2-diamine is a bidentate ligand. We can have the arrangement of this compound like this. Now in this case, we don't have any problem of a cis trans, because this type of formula doesn't show cis trans isomerism, and we can have the mirror image with the formula like this, and 3 plus. Any one of these can be minus and the other one will be plus, and these 2 will be the enantiomers. So this is what we have, the optical isomerism of the coordinate compounds.